Okay, so let's talk about alkenes. So what is an alkene? It's a hydrocarbon with a carbon-carbon double bond. Alkenes can be called an olefin as well. Olefin is just another term used to describe alkenes. Now, alkenes are wonderful feedstocks. So alkenes are a readily modified functional group, and we can use them to make aldehydes, alcohols, alkyl chlorides, vinyl chlorides, complicated polymers, epoxides. So an alkene really is a useful, easily diversified building block that is utilized in chemistry, and this alkene starting material, such as ethylene and propylene, which are obtained from cracking fossil fuels, can be converted into a range of commodity chemicals using pretty simple reactions. Okay, so moving on from the uses of alkenes, let's talk about unsaturated hydrocarbons. So hydrocarbons with multiple bonds, so these double or triple, are unsaturated. So these include alkenes and alkynes. The alkene functional group is the carbon-carbon double bond. The alkyne functional group is the carbon-carbon triple bond. Okay, degree of unsaturation describes the number of multiple bonds or rings. So remember how when I talked about drawing constitutional isomers, the number of multiple bonds or rings always stays the same in total? That's because we're actually using this idea of du when we drew constitutional isomers. So for example, for a saturated acyclic compound, we have CnH2n plus 2. Now an alkene has fewer hydrogens than an alkane because of the double bond. So if we compare, for example, an alkane to an alkene, my question to you is, how many fewer hydrogens do we have? Just looking at these two pictures, how many fewer hydrogens do we have? 2, exactly right. We can clearly see that our alkane has 2 extra hydrogens and our alkene has 2 less. So we have CnH2n. So each ring or multiple bond replaces 2 hydrogens. For every 2 hydrogens missing, there is 1 degree of unsaturation. So du can be simplified to 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of halogens. So if there are no halogens, nitrogens, or oxygen atoms, we can simplify this equation to du is 2 times the number of carbons plus 2 minus the number of hydrogens. So this C is the number of carbon atoms, and this H is the number of hydrogen atoms. Okay, wonderful. So let's look at an example. So for ethylene, our du would be equal to 2. And how many carbons do we have in ethylene? How many carbons? 2, yep. Okay, plus 2 minus the number of hydrogens. We have 4 hydrogens over 2, and that gives us a du value of 1. And this 1 tells us we have 1 carbon-carbon double bond or 1 ring. In this case, we have 1 carbon-carbon double bond. Okay, so let's keep going with this idea. So let's look at C6H10. So the du for C6H10 would be 2. So that means we can have 2 double bonds. We can have 1 triple bond. So let's put an or symbol just to say we can have either of these options, or 2 rings, or 1 ring plus 1 double bond. Okay, wonderful. So DU tells us the total number of carbon-carbon multiple bonds and or rings. So we can draw a range of structures. For example, we can have a structure with 2 double bonds, so this pentadiene molecule. We can have cyclohexene, which has 1 ring and 1 double bond. We can have this bicyclic species, which has 2 rings, or an alkyne containing species, which has an alkyne, which is 1 triple bond. So we usually need a little more data than just DU in order to determine and elucidate the exact structure of our molecule. Now, additionally, often as we'll see in this next chapter, part of the structure of a product can be inferred from the reaction conditions used. So we can use reactivity as also a gauge. This is covered more in Chem 113 when you start doing chemical tests for different functional groups. Okay, so let's look at degrees of unsaturation with other elements. So organohalogens, so your halogens, let me change the color for that. Your halogens, fluorine, chlorine, bromine, iodine. So the halogen replaces hydrogen. Okay, so in this formula, we'd use our modified DU formula where X is the number of halogen atoms. So a halogen just directly replaces a hydrogen. So if we're looking at the following formula, so C4H6Br2. So for our DU, we have 2 times the number of carbons, which is 4, plus 2. We have 6 hydrogens in our formula. Let me start with the halogens. So let's fill in the halogens. We know we have 6 hydrogens. And how many halogens do we have? How many halogens do we have in the following formula? 2. Okay, perfect. So then calculating our DU. So we have 10 minus 8 over 2, which gives us a DU of 1, which as we can see, we have 1 alkene. Oh, sorry, we have one alkene. Does that make sense so far? Okay, let's do an example now. So let's calculate the degree of unsaturation for the following formula. And then I'd like you using the annotate tool to try and draw a reasonable constitutional isomer of the following formula. So first I want you to calculate the DU for the following formula, C5H5Cl, and then I'd like someone to break out the annotate feature and try and draw a reasonable structure. If it has a ring, no alkyne. Other than that, you can get as creative as you want. So let's start with the DU calculation, and we'll come together as a group to discuss in about 3 minutes. And don't be shy if you already have the DU calculated to type it in chat, and especially don't be shy to break out the annotate tool and start trying to draw a reasonable structure. And we'll discuss in about 2 more minutes, but please don't be shy. I at least want to see a reasonable calculated DU in the chat. And if someone would like to attempt drawing a structure using the annotate feature, that would be perfect. There are multiple solutions, so don't be shy. If one of your classmates start drawing, you can also draw. I guarantee there are at least 4 or 5 different solutions for this problem. So I see in the chat a reasonable calculation for the DU, and looking at the structure, looks pretty good. Let's finish it off by adding some hydrogens, but you're spot on. You have 2 bonds and two double bonds and 1 ring, matching the DU of 3. There's one thing you're missing, which is the chlorine, but you could just put it in place of any of the hydrogens. But this looks perfect so far. Yep, exactly right, spot on. So let's now discuss. Thank you for clearing. Perfect. So let's now discuss. But these responses were perfect so far, and I see someone wrote an IUPAC name for one of their structures, so we'll entertain that option as well. So we have 2 times 5, we have 5 carbons, plus 2 minus 5 for our hydrogens, minus 1 for our halogen over 2. So we have 12 minus 6, we have 6 over 2, a DU value of 3. Okay? So we need 1 ring plus 2 alkenes if we're following the constraints of our problem. So your classmates immediately drew something that looked like this. Now, of course, it doesn't matter where you put the chlorine. In this case, I see in the chat that Mitchell proposed 1 chloro cyclopent 2,4-ene. So he's bringing up some of the nomenclature that we'll discuss in a moment. Okay, so following this naming convention, we want the chlorine at the lowest carbon locant number position. Okay, so on our first alkene. So for this name, it would probably be 1,13-ene. Unless, because the alkene already gets the lowest locant number over the chloro substituent, we'd likely have our chlorine on the alkene. So if we're naming one of the structures that we drew, you can also put the chlorine on other carbons. You're more than welcome to move your chlorine to another carbon. We'll talk more about priority and how to rank groups in terms of carbon locant priority in the next chapter, once we introduce our halogens. But as you can see, there are a range of different regioisomers and constitutional isomers for this structure, and all of them are valid. This skill of drawing skeletal structures using DU in the chemical formula will be especially invaluable in structure determination. Okay, so let's keep going. Let's continue on and let's figure out degree of unsaturation with other elements. So oxygen is divalent, right? So oxygen can form 2 bonds. So this won't affect the formula of equivalent hydrocarbons. So oxygen can be ignored in calculating degrees of unsaturation. So let's look at an example. So notice how in our modified DU formula, we don't care about the number of oxygen atoms when calculating DU. So to calculate the DU, for example, for C5H8O, our DU would be 2 times 5 plus 2 minus our number of hydrogens, which is 8 divided by 2. So this gives us 4 over 2, which gives us 2. And as we can see, how many alkenes do we have? How many alkenes do we have? 2. Okay, so all is right with the world. So let's try a problem now. So we have C3H4O. I'd like you to calculate the DU for this formula, and given that the structure contains an aldehyde, I'd like you to draw a reasonable constitutional isomer. Remember, an aldehyde looks like this. So you want to be familiar with your functional groups as they're relevant when thinking about DU. So let's take a few moments. Let's take about 2 to 3 minutes. I'd like to see a reasonable DU calculation. And then if someone would like to break out the annotate tool, and just as a reminder, it's in the meeting tab on Zoom, and it's this little pen icon. So I already see people typing a reasonable DU. So just to illustrate, we have 3 carbons times 2 plus 2 minus the number of hydrogens, which is 4 over 2. So we have a DU value of 2. Let's now get creative and let's try drawing at least one reasonable constitutional isomer for this molecule. Okay, perfect. I see there's not a lot of options for drawing structures for this case, but yes, the structure in pink was also perfect. So I see 2 structures that are perfect. I'm just going to clear them now and we'll discuss a few potential instructor solutions. So following our DU of 2, we need a total of 2 double bonds or a double bond and a ring. Whoops, let me switch to the normal interface so that way the writing's a little more clear. So what immediately springs to mind is the following structure. This is known as acrolein. It's a nice building block used for a range of cyclization reactions. Other options that are a little more esoteric would be this oh, no, can't do that. We need an aldehyde. Yeah, you're really stuck with acrolein. Yeah, there's not too much you can do with the number of carbons. So really acrolein is the only potential valid structure you can draw. Yeah. Unless anyone thinks of any other one, but no, these problems are pretty open-ended. In some cases, you're a little more constrained in the amount of potential structures you can draw. Okay. Let's look at degree of unsaturation with other elements. So nitrogen has 3 bonds, so it's trivalent. So let's use a blue color for nitrogen. So this adds 1 more hydrogen to the original hydrocarbon. Okay, so one trick that you can use is you can ignore the nitrogens and subtract 1 hydrogen for every nitrogen you ignore. So if we're writing this in a formula, you can think of DU as 2 times the number of carbons plus 2 plus the number of nitrogens minus X minus H. So let's show an example for the following formula, C5H9N. So our DU would be 2 times the number of carbons, which is 5, plus 2, plus the number of nitrogens, which is 1, minus the number of hydrogens, which is 9 over 2. So we have 13 minus 9, 4, which gives us 4 over 2, which gives us a DU value of 2. Do we have a DU value of 2 in this structure? Do we have 1 alkene plus 1 ring? Do we have 2 functionalities for our DU equation? Yes. Okay, so for nitrogen, you simply add the number of nitrogens when calculating DU. So let's just do a quick calculation. Let's not worry too much about the structure, but I just like to see a quick calculation of the DU for C4H7N. So let's spend about a minute and a half and calculate the DU. And you're more than welcome to type your response in chat or use the annotate feature, whatever you're comfortable with. Yep, I see a lot of reasonable responses. Allow me to just clear them and then I'll propose and then I'll write out the instructor response just so that way it's a little bit more legible, but these responses are perfect. So in terms of our DU calculation, we're going to take 2 times the number of carbons, which is 4, plus 2 plus the number of nitrogens, which is 1, minus the number of hydrogens, which is 7, over 2. So looking at this, we have 4 over 2, which gives us a DU value of 2. Perfect. Okay, so DU is a useful tool in limiting the number of potential options when you're drawing constitutional isomers. It can help guide your process of drawing constitutional isomers. Let's now move on to a bulky portion of this next chapter. We're dealing with alkene reactivity and alkene structure. So let's talk a little bit about naming alkenes. So you name your parent hydrocarbon chain by finding the longest carbon chain that contains the carbon-carbon double bond. Okay, so as we notice in this example, the longest carbon chain that contains our carbon-carbon double bond would be the pentene chain, not the hexane chain. Does everyone notice how the chain in green does not include our double bond? Your longest chain needs to include your double bond. Does that make sense? Okay, perfect. So the carbon numbering must start from one side of the molecule, pass through the double bond, and end at the other side of the molecule. So when counting carbons, you want to give the smallest possible locant number for the carbon-carbon double bond. And you use the lowest carbon locant number to indicate the double bond location. So for example, in this case, we put our alkene location at carbon 1, counting 1, 2, 3, 4, 5. Oops. 3, 4, 5. rather than 1, 2, 3, 4, 5. We want our alkene to have the smallest possible carbon locant number, so we number our alkene starting at carbon 1. Now, once you've dealt with the alkene, then you care about the substituents. The alkene takes priority. The substituents must have the lowest possible numbers after, and this is always important, assigning the lowest possible locant for the carbon-carbon double bond. Okay, let's keep going with this. You're going to number and name the alkyl substituents following alkyl group nomenclature rules. So you may need to look back on chapter 3 and chapter 4, and you write the substituents in alphabetical order, specifying the carbon number for each substituent. Now, if there are multiple alkenes, we name them using diene, triene, tetraene, and you need to specify the location of each double bond with the carbon number. Finally, since we have an alkene, you replace the ane ending with the locant number followed by the suffix -ene. Okay, so let's look at our numbering here. So the numbering in red is correct. The numbering in blue is another option. 1, 2, 3, 4, 5, 6. Would someone like to tell me which number is smaller, 2 or 5 for our alkene? Which number is smaller, 2 or 5? 2. So we name this as hex 2-ene. Hex because we have 6 carbons, 2 because our alkene starts at carbon 2, and then ene because we have an alkene. Okay, let's look at other options in blue for this second structure. 1, 2, 3, 4, 5, 6. Okay, so what is the smallest locant number we can give our alkene? 3 or 4? Are we counting in red or blue? Which numbers are smaller for our locant number for our alkene? Well, 3 is smaller, and we have 2 options now. So we have a tie. Red and blue both are counting from 3. However, now we have to look at our next substituent. And thinking about our methyl group, which number would be smaller for our methyl group, 2 or 5? What's smaller for our methyl group? 2. Okay, so we name this as 2-methyl hex 3-ene rather than 5-methyl hex 3-ene. Let me just cross that out. So we want the smallest locant number for our alkene. If it's a tie, then and only then do we look at our substituents. Does that make sense? So this is an example of a tiebreaker where our substituent numbering breaks the tie. Does that make sense? Perfect. So let's name the following molecules, and we'll do the first one together. So first and foremost, I need to find my longest chain. And there's a really nice trick for this. So what you do is you look at all of your substituents around the alkene and you find the longest substituent, the longest chain on each side of your alkene. So I'm going to arbitrarily circle this chain. Okay, so that's one. I'm going to put a star next to it. Here's the other. Okay, we don't have to worry about Z or E because these two chain substituents are identical. I did that intentionally to save you some grief. Okay, now let's try to circle our longest chain. So I have my longest substituent. So now I'm going to circle my longest chain. Next, what I'm going to do is I'm going to propose a numbering scheme. So 1, 2, 3, 4, 5, 6, 7. That's one numbering scheme. Let's try my other numbering scheme, counting from right to left. 1, 2, 3, 4, 5, 6, 7. Okay, now let's compare. So in blue, we have 6-methyl, 3 heptene, hept, because we have 7. In red, we would have 2-methyl, 4 heptene. Oh, wait, we're missing the ethyl group. We're missing the ethyl group. Hold on. One moment. In blue, sorry. So we have 3 ethyl. So this is an ethyl group. This group is a methyl group. So 3 ethyl, 6 methyl, hept, 3 ene. So that's what we get in blue. Now let's do the red numbering convention. In this case, we'd have 5 ethyl, 2 methyl, hept, 4 ene. Now, when we talked about the preferred naming method, we care about our alkene numbering first and foremost, and which counting method gives us the smallest alkene locant number. Which method gives us the smallest alkene locant number? Blue. So the blue name is preferred. Let me just add the dashes here. Remember, why do we have ethyl in front? We go in alphabetical order. So the beautiful and the fun thing about this kind of naming example is that your substituent numbers do not matter as much as your alkene carbon number. The alkene is the higher priority substituent in terms of naming. Is everyone comfortable with this example? Did everyone understand what I did? I found the longest chain. I wrote both of my numbering methods out. I numbered and wrote out the locant and the name for each substituent. Then I compared my alkene locant number. The blue naming convention had the smaller alkene locant number, ergo it was preferred. So the name for this would be 3. Whoops, give it one moment. Let me reset OneNote really quickly. Sometimes it gets a little bit overwhelmed when I try to write things too quickly. So let me just reset. So you should be seeing the OneNote screen. So let's now write out the complete name for this structure. So this is 3-ethyl, 6-methyl, hept, 3-ene. Okay, let's do one more together. So our longest chain, well, that's pretty self-explanatory here. The longest chain would be 4 carbons. Now, there is some debate that we need to consider whether the chain in red or blue should be chosen. My question to all of you is, following our rules, which chain should we write as our longest chain, red or blue? Blue, overwhelmingly. The reason being, you need to include both of your alkenes or all of your alkenes in the chain. The longest chain has all of your alkenes present. Now, what we're going to do is we're going to provide 2 numbering conventions. So in blue, we're going left to right. In red, we're going right to left. Okay, so in red, we have 3-methyl, 1,3-butadiene. But, because we have 4 carbons in our chain. In blue, we have 2-methyl, 1,3-butadiene. Which of these naming conventions is preferred, red or blue? So we have a tie between our alkene numbers. So now we look at our substituents and which naming convention, red or blue, gives us the lowest substituent numbers. Right? So the blue name is preferred. Okay. Let's do one more together. And this is where Marvin's sketch is really helpful, since it will actually give you the name of any structure you put in, and it makes your life so much easier if you're practicing nomenclature. So let's look at the following example. So this is a cyclic species, okay? So we have a few potential numbering options. So our longest chain obviously is going to be our cyclohexene ring. So we have 1, 2, 3, 4, 5, 6. Alternatively, we can start counting at the other end of our alkene. 1, 2, 3, 4, 5, 6. So in blue, we would have 2-methyl cyclohex 1-ene. Alternatively, in red, we'd have 1-methyl cyclohex 1-ene. And which of these naming conventions are preferred, blue or red? Sorry, what was that? Oh, Carter, to answer your question, there are 2 ethyl groups in our first molecule. And so I see a lot of people typing red. That's exactly right. The red naming convention is preferred because it gives the smallest locant number to our substituents while having our alkene locant number tied. Does that make sense to everyone? Is everyone comfortable with these examples? Any questions on these names? Any questions on these names so far? Just as a side note, for this butadiene, I've been naming it in a little bit of an old school way. The slightly more modern way to name this would be 2-methyl buta 1,3-diene, both of which are reasonable methods for naming this diene structure. Any other questions with regards to these naming examples? Any other questions with regards to these naming examples before I let you loose to work on your own naming problems? Okay, if there aren't any other questions, I'm going to let you loose on the following 3 molecules. As a refresher, for 5 carbons, it's pentyl, and 6 carbons is hexyl. Essentially, you take the main chain stem and you replace the ending with YL. Okay, so let's work on these 3 examples, A, B, and C. Let's spend about 5 to 6 minutes on each of these examples, and I'd like you to come up with a name for each of these alkenes. You're welcome to message me your proposed name for each of these alkenes in the chat. And don't be shy to write your proposed name for each of these structures. Or to start off the discussion, you can even try to circle the longest chain using the annotate feature, just so that way we can have a discussion. So I already see some reasonable names proposed in the chat. Let's get a few more responses for each of these structures and then we'll discuss. And just remember that your numbering for your longest chain should include the alkene. Yep, I see a lot of reasonable responses and annotate for the longest chain. Now let's focus on naming these structures. I see some reasonable responses for structure A. Let's get a few more responses for structures B and C. So for structure C, it's almost perfect. You just need a prefix to tell me that there are two methyls. And what do we call that prefix? Yep. For B, yep, the name for our longest chain will have a cyclo prefix. Yep, I see a lot of reasonable responses so far. I would just check the carbon locant numbers for proposed for structure B. But otherwise, I'm seeing a lot of reasonable responses. Let's try to get a few more responses for structure B, and let's try thinking about the carbon locant numbers for the diene. Yep, I see a lot of reasonable responses for structure B, A, and C. Perfect, so all of them are spot on. So let's discuss. I'm just gonna clear some of this annotation and we'll start with the instructor solution just so everyone has a clean batch for their notes. So circling the longest chain, that was exactly right. The longest chain includes our alkene. Next, we provide our numbering convention. So we count such to give the smallest locant number for our alkene. This substituent is an ethyl group. So we name this as 2-ethyl. 5 is pent. So this would be pent 1-ene. It also is sometimes brought up that you can name it as 2-ethyl 1-pentene. Both are correct. This method is a little bit newer. So depending on how old the chemist is, they may name things in a slightly different way. So in terms of numbering for this diene, so we start at this carbon, and when you're counting, you have to count through your alkene from one side of the molecule to another. So we can count clockwise through our alkene or counterclockwise through our alkene. In either case, the start of our alkene would be at carbon number 1 and carbon number 4. So we call this cyclo, because it's cyclic, hex, and then it's hexa. And since we have two alkenes at positions 1 and 4, we call this cyclohexa 1,4-diene. It's also reasonable to call this 1,4-cyclohexadiene. Both are reasonable. For our last structure, structure C, let me just get the zoom in just right. Okay, perfect. So we find our longest chain has our alkene, and then we have two numbering conventions. 1, 2, 3, 4, 5, 6 in purple, or an alternative numbering convention in blue. The numbering convention in blue is preferred because it gives the smallest locant number to our alkene. We have two methyl groups, so we call this 2,4, and since we have two methyl groups, we use the prefix di. So this is 2,4-dimethyl. 6 carbons is hex, and then we specify that it's at carbon 2, so this would be hex 2-ene. Perfect. Okay, let's now take a moment. Now that we've done a few examples, if you have any questions, now would be a great time to ask, but let's now tackle structure D. Let's revise, now that we've had the opportunity for revision and correction. Let's try structure D, and let's propose a reasonable name for structure D. Remembering that when numbering, you count through your alkene for cyclic systems, either clockwise or counterclockwise. Structure D is more tricky than you think, so just be careful with it. It's nothing we can't handle, but just be meticulous when you think about the rules for substituents and what's preferred in naming in terms of locant numbers. So I'll give everyone about 2 to 3 minutes on this problem. Oh wow, I already see someone beginning to write out their proposed solution. And the locant numbers look promising so far. And you're more than welcome to type your response in chat as well. So there's a small disagreement. We have some of our students proposing 1,5-dimethyl pent-1-ene and other students proposing 2,3-dimethyl cyclopent. So the cyclopent-ene base chain is correct, but in terms of locant numbers, let's entertain both of these possibilities and let's discuss. So let's start with the proposal that we received for 2,3. So starting off, we want the smallest possible locant number for our alkene. So we'll put it at carbon 1. Okay, wonderful. So when counting, you have to count through your alkene. So we have to count through our alkene counterclockwise, 1, 2, 3, 4, 5, or alternatively, we can start on the other side of our alkene and count through our alkene. Clockwise, and blue is counterclockwise. Okay, you cannot, in terms of counting, just count from the start of our alkene and not count through. When deciding your carbon locant numbers, you must count through the alkene. Does that make sense to everyone? So we cannot just cherry pick and go, oh, I see in both the methods, everyone counted through the alkene. Perfect. So I didn't see any 1,2 dimethyls, so that's good. Now let's move on to our next order of business. I'm going to write both the names out and then we'll compare them. So in this case, we have 2,3-dimethyl cyclopent 1-ene. Wonderful. It's good that we didn't make the first mistake I commonly see. And the other option is 1,5-dimethyl cyclopent 1-ene. Now my question to all of you, and let's look at our first locant numbers. What is the smaller locant number, 1 or 2? So remember in nomenclature for substituents, do we care about the smallest average locant number or the smallest from start to finish locant number? From the start, right? So does 1 win out over 2 for our locant numbers? Does 1 win out over 2? Yes. So then the proposed name in purple, 1,5-dimethyl cyclopent 1-ene, is the correct IUPAC name. And it's just because for numbering substituents, you choose the substituent carbon locants that give in sequential order from your first substituent to your last, the lowest number. It's not the average number, it's just from first to last. So even though 5 is a larger number than 3, it doesn't matter because our first locant number is smaller. Does that make sense to everyone? Any questions on this example? And just as a reminder, if you have Marvin sketch, you can draw whatever structure you want and you can try naming it. And Marvin sketch will actually spit out and provide you the name for any molecule you put in, including stereochemistry naming. And we'll talk about that actually right now. So, while we're on the topic of nomenclature, let's talk a little bit about naming haloalkenes and haloalkanes. Okay, so if you're naming just an alkane, you want to choose the longest chain containing the alkyl halide. However, and this is really important, double or triple bonds take precedence, take priority over a halogen or alkyl group. So in terms of priority, first and foremost, you deal with your alkene or alkyne, and then, and only then, do you care about assigning the smallest locant number to your halogen. So we're beginning to introduce this idea of functional group priority in nomenclature rules. So you count carbons, so your substituents have the smallest possible locant numbers. In the event of a tie, you assign the smallest locant numbers based on alphabetical order. You name each halogen and each alkyl group alphabetically, specifying the locant number for each. So halogens don't get a special suffix. Halogens You just name them like an alkyl substituent. If there are two or more halogens that are identical, you indicate the position of each and you use di, tri, tetra, etc. So to give you an example here, this would be 5-bromo 2,4,4-trimethylheptane. So the halogens have the same priority in naming as alkyl groups. So let's look at our two options in blue and red. So the longest chain is pretty straightforward, just from left to right or right to left. In terms of our carbon locant numbers, we can either count from left to right in red or right to left in blue. Okay, that's all fine and well. My question to all of you is, let's now look at our proposed names. So first, we have our name in red, and I'm going to name the structure in blue. So we have 3-bromo 4,4,6 trimethyl heptane. Now, if we look at our locant numbers, which naming convention gives us the smallest locant number? The 3 observed in blue or the 2 observed in red? Which numbering method is preferred, blue or red? Which numbering method gives us the smallest overall from start to finish locant number? The smallest from start to finish locant number. So if we compare our first locant number, red gives us the smaller locant number, so red is preferred. Does the bromine matter? Do we care about the bromo substituent? Do we care about this bromine any more than a halogen? No, it has the same priority. You just want the smallest from the first locant number to the last. Okay, so let's keep going with this. And let's look at a few more examples. We'll do these examples together, and then I'll let you loose to handle a few examples on your own. So in this case, we have 1-chloro-3-methyl cyclohexane. So the longest chain, don't have to worry too much about that. So there are 2 numbering conventions, in red, which is clockwise, or in blue, which is counterclockwise. So in blue, we get 1-chloro-3-methyl cyclohexane. In red, we get 3-chloro 1-methyl cyclohexane. Now, looking at our first locant number, we have 1 and 1. Our second locant number, we have 3 and 3. It looks like a tie. What is our tiebreaker? If our locant numbers are the same, what breaks the tie? What do we care about next? Well, the first number is the same, and the second number is the same, but what do we care about then? What's our tiebreaker? If our locant numbers are the same, we want the alphabetical order. Exactly right. Thank you. So we name this 1-chloro because the C is alphabetically before M. So 1-chloro 3-methyl cyclohexane is the correct name for this structure. Yep, exactly right. Exactly right. Yep. You put your substituents in alphabetical order, and if there's a tie in locant numbers, you put the smallest locant number at the first species in alphabetical order. Does that make sense? Perfect. So let's keep going now, and let's see. I have a fair list of compounds for you to deal with. So let's now try naming, and I'll start us off with a name of a first few batch, and we'll work on these examples together. So looking at the following molecule, our longest chain is obvious. We don't have to worry too much about that. Now we have to consider carbon counting. We can count 1, 2, 3, 4, or 1, 2, 3, 4. Now, it's at this point that we're going to need to write out our proposed names. So we can have 2-chloro butene or 3-chloro butene. And which method wins out? Blue or red? Blue or red? Blue. Why? Because blue assigns the smallest possible locant numbers to each of our substituents. Now, and this may be a bit of a leading question. Is this name finished? Is this name finished? Considering what we learned last chapter, we learned all of these different ways of classifying alkene stereochemistry. Is this name complete, or would someone like to add something to this name? Let's think about that for so R and S applies to sp3 centers, but we have another naming convention that we use for alkenes, Z and E, right? So let's talk about that. Yep, this would be 2Z. Yep. So let's explain what's going on here. Man, my 2's and Z's look too similar. So 2Z, there we go. So in terms of priority, so I'm going to erase this blue and red to avoid creating too much confusion. And now we're going to focus on priority. So on the left-hand side of our alkene, what's the highest priority group? Hydrogen or methyl? What's the highest priority group? Hydrogen or methyl? Methyl. Okay. And chlorine or methyl? What's higher priority? Chlorine or carbon? Chlorine. Okay. Our two priority groups that are high priority are on the same side. So do we name this as Z or E? If they're on the same side, is that Z or E? Z. Yep, so this is 2Z. So this 2Z is saying our alkene starts at carbon number 2, which it does, and is Z in configuration. Does that make sense to everyone? Does everyone understand why we need to specify stereochemistry in this case? Because we have an alkene with 4 different substituents, or we have an alkene with enough different substituents on each side. Z is essentially telling us, so in cases where we have multiple substituents, Z is saying that that our high priority groups are on the same side. They're on the same side of our alkene. It is best thought of as the IUPAC way of describing cis substituents, except Z and E notation can be applied to alkenes with multiple substituents more readily. Does that make sense? It's essentially saying our high priority groups are cis. Yes, exactly right. If we swapped the methyl and the hydrogen, it would be E. And we'll actually see an example of an E alkene. Does that make sense? Does this look familiar from the last chapter when we discussed alkene stereochemistry? Perfect. So let's take a moment. We'll worry about Z and E at the end of our name, once we're done with everything else. So the longest chain is obvious, and let's consider our two possible naming conventions. So we can count right to left or left to right. Okay, so let's write out both the names. So I'll write out the name in blue first. So we have 4-bromo, 1, 2, 3, 4, 5, 6, hex, 2-ene. Okay, and the other option would be 3-bromo, hex, 4-ene. Okay, so now that we have our two options established, which one do we like more according to our naming rules? Blue or red? Which one is preferred according to our naming rules? Blue. And the reason for that, again, is we want the smallest possible alkene locant number, and 2 is lower than 4. Does that make sense? Is everyone comfortable with our basic names so far? Okay, now I'm going to erase. And we're going to focus on priority. So we're going to draw out our hydrogens. So on the left-hand side, what's our highest priority group? Carbon or hydrogen? What wins out? Carbon or hydrogen? What wins out? What's higher priority? Carbon, yep. So carbon is priority 1. On the right-hand side, what wins out? Carbon or hydrogen? Carbon. Okay, so are our substituents on the same or opposite side of our alkene? Are they Z or E? E. So we would call this, we put the locant number of our alkene, so it's at carbon 2, so we call this 2, followed by the stereochemistry. So this is 2E, 4-bromo, hex, 2-ene. And again, I can't stress this enough. If you want to practice this thoroughly, and if you want to get a sense of how questions are made in the book, they literally just put a structure into a structure drawing tool, and they say, okay, structure drawing tool, tell me the name. And checking using Marvin Sketch on my separate screen, we have a perfect match. Yep. You technically in the name don't have to have this dash after the chloro. If you're so inclined. No, it's not required. Okay, let's do one more together before I let you loose on a few examples to close out this period. So in this case, we have the following molecule. let's try using our two methods of counting. Remember, you always have to count through your alkenes. We have 1, 2, 3, 4, 5, 6 in blue, counting clockwise, or in red, counterclockwise. Of course, there are other ways of counting, but I'm just simplifying it to these two most logical methods. So in our first name, we have 1 bromo cyclohexene. And then in blue, we have 3 bromo cyclohex-1-ene. And which method is preferred, blue or red? Which method is preferred? What is higher priority? The method in blue is overwhelmingly preferred because you want your alkene to have the smaller locant number. Now, the beautiful thing about dealing with cyclohexane rings is that there is no trans small rings. So anything less than 7 carbons about, you're not going to see a trans ring. Let's just do 8 carbons just to be consistent. So the small rings can't be trans. You could prove this to yourself by making a model kit, but it's like geometrically impossible to have a trans alkene. So you don't have to worry about Z or E for cyclic alkene. Does that make sense to everyone? Can everyone visualize, or do you want me to bring a model out to show that you can't have a trans alkene in a 6-membered ring? Let's show that just briefly. Okay, so this is what a trans alkene looks like. As you can clearly see, it's not geometrically stable. So you don't have to worry about Z or E for cyclic alkenes because it's geometrically not allowed. This thing is ridiculously strained and it doesn't exist. So yes, you can technically consider the ring substituents as Z, but you don't have to specify it because you'll never see an E alkene in a 6-membered ring. It's so high in energy, it never forms. Does that make sense? Okay, so in our last few minutes, just to close out our discussion, let's name the following 3 compounds, and I'll give everyone about 4 to 5 minutes, and then we'll come together as a group to discuss. You're more than welcome to write your proposed name for each of these structures, and then we'll come together to discuss at the end of this 5-minute problem-solving period. And don't be shy to message me any questions or attempt to circle the longest chain or for the proposed numbering convention using the annotate tool. And don't be shy to annotate in whatever structure you prefer. You don't have to go from A to C. You can start in whatever order you want. And try naming your substituents. You can even try writing both the names possible for B and see which one is preferred. You're on the right track, certainly. I find it's easier to make a choice once you have both the proposed names written, and then you can see using our naming rules which name is preferred. The numbering method in yellow looks good so far. Let's get one or two responses, and let's get a few full names for each of these structures. And don't be worried too much if your name is perfectly correct. Let's just get some proposed responses so that way we can discuss. And we'll discuss in about another 2 to 3 minutes. I see some reasonable names proposed for structure A. Let's get some proposed names for structures B and C. Oh, no, the name proposed for A is perfectly reasonable. Let's get a few proposed names for B and C, either in the chat or using the annotate feature. Yep. Okay, I see some reasonable responses for structure B. Is someone brave enough or is someone willing to tackle structure C? This case, the name has one last little trick to it that you need to pay attention to, because that, well, thankfully the alkene doesn't have any stereochemistry, but you just need to be careful with finding the longest chain. I see some reasonable responses for B. Let's get some reasonable responses or numbering for C, and then we'll discuss all of these examples together. Okay, so I see some reasonable responses. So I'm just going to clear the annotations and let's discuss as a group. Okay, so first and foremost, looking at structure A, the longest chain is pretty straightforward. We'll look at two proposed numbering methods in blue and red. So in red, we have 2-chloro, 4-methyl, hex, 5-ene. In blue, we have 5-chloro, 3-methyl. Yep, that proposed response is correct. Hex, 1-ene. Let me just clear annotations. Give me one moment. Yes, but that response is perfectly correct. And comparing our two proposed names, which numbering method is preferred, in blue or in red? Which numbering method is preferred? Blue. Yep, it gives the smallest locant number to our alkene. Okay, let's discuss now the cyclic system. So counting through our alkene, we can either count clockwise in red, which would give us 3-chloro, 4-ethyl, cyclohex, 1-ene, or we can count in blue clockwise and give us 5 chloro, 4 ethyl, cyclohex, 2 ene. And which method is preferred in, cyclohex 1 ene. So which method is preferred in blue or in red? Oh, right, this is 5 carbons. I think I got that mixed up with, this would be cyclopent for our 5 carbons. There we go. Okay, so now comparing our naming methods in blue or in red. First, our alkene locant numbers are the same. Now we look at our first substituent, our first locant number. So what is lower, 3 or 4? What's the lower locant number, 3 or 4? 3 is lower, ergo the name in red is preferred. Does that make sense to everyone? And I see a lot of students have proposed that name for structure B in the chat. So that proposed name is perfect for structure B. Any questions so far? Okay, let's keep going. So for structure C, our longest chain has the most carbons and contains our alkene. Okay, so now let's look at 2 numbering conventions, 1, 2, 3, 4, 5, 6, 7. Thankfully, our alkene doesn't have any stereochemistry. 1, 2, 3, 4, 5, 6, 7. Okay, so in red, we'd have 4 ethyl, 3,5-dimethyl, 5-iodo. Oh, sorry. Whoops. The iodo should be before methyl. 5-iodo. And it should be 3,6-dimethyl. And this would be hept 5-ene. That's quite a mouthful. Let's try the counting method in blue. In this case, we'd have 4 ethyl, 3-iodo, 2,5-dimethyl, hept 2-ene. And which naming method is preferred, blue or red? What naming method is preferred for this structure? Blue. And in fact, a student has provided almost a perfect name for the following structure in the chat. So we've wrapped up and we've covered alkene and alkyl halide nomenclature. What we're going to do is in laboratory, we're going to take a quick 10-minute break. So I'll see everyone in lab at about 7:10. We'll continue on with this lecture and we'll discuss reactions of alkenes. The plan for this week in laboratory is to continue on with our lectures so that way we're caught up and ready for next week and eventually the final. So I'm going to stop the recording